Welcome back to the deep dive. We are tackling something today that feels infinitely complex, yet we use it to order pizza, translate menus, or check the weather without even blinking.
Hmm.
I'm talking about the engine under the hood of natural language processing.
It is. It's the machinery that lets a pile of silicon and copper make sense of, Shakespeare, or at least understand your emails well enough to suggest a reply.
And we're basing this discussion on a text by Christer Samuelson and Sanjay Tajner, which looks specifically at the statistical side of things. What struck me immediately reading this is the massive shift in philosophy the field has gone through.
Right.
I always just assumed teaching a computer English was like teaching a kid grammar. Sit down, learn the rules, memorize exceptions.
Don't dangle your participles. Yeah, that was a dream for a long time. We call that the rationalist approach. Linguists thought if they could just write down every single rule.
Every I before E except after C.
Exactly. Every conjugation, every obscure clause structure, they thought they could model language perfectly. That language was this clean, logical system.
But it turned out to be a trap.
A massive trap, because language isn't clean logic. It's messy, it's biological, it's chaotic. Those rule-based systems, the text describes them as brittle.
Brittle, okay.
You give it a sentence that breaks a rule, which humans do constantly, and the whole system it crashes. It gives you nothing. So the shift the source describes is moving from that strict school teacher model to something more flexible.
And that's where the empiricist approach comes in, the data-driven era.
That's the big pivot. Instead of telling the computer the rules, we just feed it massive amounts of text, thanks, mostly to the World Wide Web, and we say, you figure it out.
We let the machine find the patterns itself.
We do.
Yeah.
We let it find the patterns using statistics. We stop being the legislating grammarian and start being the observing statistician.
So the mission today is to unpack that toolkit. The text calls it a heterogeneous collection, which I think is a polite way of saying it's kind of a grab bag of math tricks.
It is, yeah. It ranges from, simple coin flips all the way up to complex calculus.
So we need to understand how we get from heads or tails to translate this from French to English.
And to do that, we have to start at the very, very bottom. The atomic unit of this field isn't the word or even the sentence. It's the probability measure.
The text goes right back to high school math here, but with a specific twist. They talk about the sample space. Can you ground that for everyone?
It's a simple concept that gets used in really complex ways. The sample space is just the list of everything that could happen in a scenario. You flip a coin, the space is just 2 items. Heads, tails.
Roll a die, it's 1 through 6.
1 through 6. Simple.
But here's where the text gets interesting. They bring up the Bernoulli distribution. Now, I've heard of this, but usually my eyes just glaze over. Why does a linguist care about Bernoulli?
Because it lets us abstract away. This is a key insight. When we model a coin flip with a Bernoulli distribution, we strip away the physical world. The text actually has this great aside where they say, we're explicitly ignoring the coin landing on its edge.
Or a bird snatching it out of the air.
Right. No bird interference in the model. We keep it clean.
I appreciated that.
We reduce the whole messy physical world to a single parameter, p. If p is the probability of success, then 1 minus p is the probability of failure. That's it. We stop caring about the coin and we start caring about that binary choice.
And in language, that binary choice is happening all the time.
Constantly. Is this word a noun or not? Is this the end of the sentence or not? Is this email spam or is it not? It all starts with that simple coin flip model.
Okay, so we're building up from these binary choices,
Yeah.
But then we hit this buzzword that's everywhere in tech, entropy. Usually I associate entropy with physics, the universe cooling down, things falling apart.
And in information theory, which is what we're doing here, entropy isn't really about chaos in that destructive sense. It's about surprise. Or, more specifically, unpredictability. The text defines it as a measure of how much information is in a message.
The source links this to bit length, which I found really helpful to visualize.
Yeah, think of it this way. If I have a coin that's rigged to show heads 99% of the time and I flip it, are you surprised when it's heads?
Not at all. I'd bet on it.
So that event has very low entropy. It carries almost no near information because you already knew what was likely to happen. If you were sending me the results over a text, You wouldn't need many bits of data to describe it because it's so predictable.
So if the coin is perfectly fair 50-50,
Now you have no idea what's coming. That is maximum entropy.
because I am maximally surprised by the outcome, since I couldn't predict it at all.
Correct. You need more bits of information to describe that result because the result could really be anything.
Okay, so applying this to language, if I say the United States,
Low entropy. The next word is almost certainly America. The machine is bored. It knows what's coming.
but if I say the quick brown, well, could be fox, could be dog, could be anything.
Much higher entropy. And the machine uses this measure to figure out which sequences of words are likely and which are just gibberish. It's basically trying to minimize its own surprise. A good language model is one that isn't surprised by valid English.
Which leads us to the idea of a stochastic process.
Which sounds intimidating, but it's just a fancy term for a sequence of those random choices. Language isn't one coin flip, it's a whole stream of them, one word after another, flowing through time.
And this brings us to one of the biggest concepts in the text, the hidden Markov model, or HMM. And to explain this, the authors use a very specific sentence. John seeks a unicorn.
A classic example. So let's look at this from the computer's perspective. It sees John, then seeks,
Right.
then A, then unicorn. The computer's job is to understand the structure. Maybe it wants to know that John is a noun and seeks is a verb.
The problem is, if the computer tries to look at every single word that came before unicorn to figure out what it is, the math just, it explodes, right?
It's a combinatorial explosion. If you try to track the relationship of every word to every other word in a book, you'll run out of computing power instantly. The history is just too heavy.
So we cheat.
We cheat. We use the Markov assumption.
Okay.
We assume that the probability of the current word depends only on the word right before it.
The amnesiac model.
That's a great way to put it. The model has total short-term memory loss. It looks at unicorn, and it only cares that the word before it was A. It's completely forgotten about John, or seeks.
That seems incredibly stupid. I mean, human language relies on things that were said 3 sentences ago, let alone 3 words ago.
It is stupid. The text openly calls it a naive model. So
Yeah.
here's the kicker. It works surprisingly well.
Really?
For things like speech recognition, this bigram model, just looking at pairs of words, is incredibly hard to beat for raw efficiency. It captures just enough local context to make sense of the immediate structure.
So it trades perfection for solvability. It makes the math easy enough to actually run.
Precisely. Now, there's a second layer to this, the hidden part of the HMM. In our sentence, John seeks a unicorn, the words are visible. We call them emissions.
Okay.
But the grammatical tags, noun, verb, determiner, those are hidden states. We can't see them directly in the raw text.
So the HMM is like a detective.
Mm-hmm.
It sees the footprints, the words, and tries to figure out who made them, the tags,
And to do that efficiently, it uses something called the Viterbi algorithm.
which the text describes as a dynamic programming algorithm. How should we visualize that?
Think of it like a GPS finding a route across a city. You have a grid of possible tags for every word. There are thousands of possible paths through the sentence.
And checking every single path would take forever.
Forever. Viterbi is a way of pruning the dead ends immediately. If it sees the word the, it knows it's almost never a verb, so it just kills that path right there.
I see.
It calculates the most likely path step by step, discarding the unlikely ones as it goes, so it doesn't have to check every crazy combination at the end.
But we established that the Markov model is an amnesiac. It can't see the big picture. And the text brings up a counterexample where this really fails.
Right. The English constraint grammar parser. Imagine a rule that says something like, this word can't be a verb if there's a certain type of word somewhere to the left.
Somewhere to the left.
Yeah.
That's the key. It could be 10 words back.
Oh.
Markov model can't see that far.
It's invisible to an HMM. So when we need to account for these heterogeneous information sources, clues scattered all over the place, we need a different tool.
And that's where maximum entropy models, or maxent, come in.
It's a much more flexible alternative, and the philosophy of maxent is, well, it's pretty deep. It basically says, I will model everything I know for a fact, and for everything I don't know, I will assume nothing.
Break that down. That sounds almost philosophical.
It is. It has 2 requirements. First, the model has to match the empirical distribution. So if our training data shows that the is followed by a noun 40% of the time, our model must make that happen 40% of the time.
Okay, so don't contradict the data. That's rule 1.
But there are an infinite number of mathematical models that could match that constraint. So the second rule is, Of all those possible models, you choose the one with the highest entropy,
The one that's the most random.
the one that is the most unbiased. If the data doesn't give us a reason to prefer option A over option B, we have to treat them as equal. We don't smuggle in our own secret assumptions. We keep the distribution as flat as uniform as possible, given the facts we know are true.
I see. It's the most honest model. It only knows what it's been explicitly told.
And mathematically, this results in a kind of voting system of weights. The text calls it a Gibbs distribution. Instead of a simple chain, you have all these features. The previous word was the word ends in ning, and each feature gets a weight.
And they all vote on the answer.
Exactly. The Maxent model sums up all the votes to give you the final probability. It can handle all those messy, overlapping clues that would confuse a simpler model.
So we have HMMs for sequences, Maxent for complex features. But both of those assume we have good training data, right? That somebody's already tagged John as a noun so the computer can learn.
Yes. Annotated data is gold in this field, but it's incredibly expensive to produce.
What happens when we don't have it? The source brings up machine translation. IBM Model 2.
This is the latent variable problem. Imagine you have a sentence in French, le chien est noir, and in English, the dog is black. You know they mean the same thing, but the computer doesn't know that chien aligns with dog.
That alignment is missing information. It's latent.
It's a chicken and egg problem, really. To learn the translation, you need the alignment. But to get the alignment, you need to know the translation probabilities.
So how do you break that loop?
You use the EM algorithm expectation maximization.
Which the text describes as a successive substitution algorithm.
Think of it as a refined guessing game. It's a two-step loop. Step one is expectation. You make an initial guess. You might assume, say, that every French word is equally likely to match every English word.
A terrible guess.
A terrible guess, but it's a start. You use that guess to count up the evidence in the data. Then comes step two, maximization. You take those counts and you ask, okay, based on this evidence, what are the new, better probabilities? And you update your model.
And then you just loop back to step one with the better probability.
You loop over and over. Each time, the alignment gets a little better, which means the probabilities get a little better, and you keep going until the numbers stop changing, until the system is self-consistent.
There was a quote in the text about this from Slavic Cats that made me laugh.
Oh, yes. He said the EM algorithm is like self-satisfaction.
It is better than nothing, but pales in comparison to having actual annotated data.
It's a bit of a burn, but it captures the reality of it. EM is what you use when you don't have the luxury of a human teacher. It's statistical bootstrapping. You pull yourself up by your own bootstraps with math.
Now, speaking of data issues,
Yeah.
sometimes the data isn't just missing, sometimes it's just plain wrong. The outlier problem.
This is huge. Real-world data is dirty. The source gives this great numerical example. Imagine you've got a list of measurements, 1.1, 1.2, 1.3, and then someone forgets a decimal point and just types 10.
If you take a simple average, being that the 10 just destroys your result, I think the text says the average jumps from 1.5 all the way to 2.35.
Exactly. Standard statistics based on the bell curve, the Gaussian distribution, are terrified of outliers. The bell curve assumes extreme events are basically impossible, so when it sees a 10, it panics. It tries to shift the whole model to accommodate it.
Which ruins the model for a 99% of good data. So how do we fix it?
We need robust estimation, and the hero of this story is the t-distribution.
Student's t-distribution. I have to pause on the name. Student. It sounds like a humble brag, but it's a pseudonym, right?
It is. The author was William Gossett. He worked for Guinness, the brewery.
In Dublin. Reasons best explained over a pint of Guinness, the text says.
He was dealing with really small sample sizes in brewing chemistry, yeast counts, barley quality. He couldn't use the standard big data math because he didn't have big data. So he developed a distribution that has fatter tails than the bell curve.
Fatter tails, that's the key visual, meaning it sort of expects weird things to happen more often.
Exactly. A Gaussian curve drops to zero really fast. It says extreme things don't happen. The t-distribution says, hey, sometimes crazy things happen. It has more probability mass out at the edges.
So when it sees that 10, it doesn't panic.
It just shrugs. It assigns a higher probability to that data point just being an outlier rather than letting it drag the average of the whole group. It basically says, that's probably a mistake, and it keeps the average closer to the real data.
The text makes a connection to finance here that was pretty startling, the whole Six Sigma event thing.
Right. Under a normal bell curve model, a market crash of a certain size should happen, once every billion years. But under a Cauchy distribution, which is a type of t-distribution, the odds are more like 10 to 1.
That explains a lot about the stock market. But in NLP, this just means our spell checker doesn't have a stroke when we make a typo.
It keeps the system robust against garbage data. One bad input doesn't wreck the entire learning process.
So we've built this stack. We have probability for the basics, HMMs for structure, maxent for complex clues, EM for missing data, and robust estimation for errors. But how do we know if any of it actually works?
The evaluation phase, this is critical. You can't just say, it looks good.
The text rattles off accuracy, precision, and recall.
Accuracy is simple. How often did you get it right? But precision and recall are more nuanced. Precision is, of all the things I claimed were right, how many actually were? And recall is, of all the things I should have found, how many did I miss?
So it's the difference between being careful not to make a mistake and being careful not to miss anything.
But then they ask a deeper question. Do humans even agree on the answer in the first place?
Inter-annotator agreement.
Yeah.
If you give a complex sentence to two different linguists to tag, will they give you the same answers?
And often, the answer is no. Language can be subjective. And if humans can't agree, the computer has a hard ceiling on how well it can do. We use a statistic called Cohen's kappa to measure this. It calculates the agreement, but it subtracts out the agreement you'd expect just from random chance.
So it's the true agreement.
Right. If your kappa score is low, it means the task itself is subjective or maybe just poorly defined. You can't really blame the algorithm if the problem is fuzzy.
And finally, the text warns us about the null hypothesis.
Significance testing. This is the final reality check. Just because your system A gets a score of 85% and my system B gets 86% doesn't automatically mean B is better. It could have just been luck on that particular test set.
You have to prove it's not a fluke.
You have to. We use things like the t-test to make sure the improvement is real and repeatable. We have to statistically reject the idea that our result was just random noise.
We've covered so much ground. It's amazing to think that when I speak to a digital assistant, all of this is happening under the surface. The coin flips, the amnesiac guessing, the robust filtering.
It really is a whole toolbox. And the source concludes with this interesting thought about statistical purism. We want to be mathematically rigorous. We want everything to be clean and derivable from first principles.
But language isn't clean.
No. So the experts in the field admit that it relies heavily on the black art of probability smoothing.
I love that phrase, black art. It sounds like magic.
It's an admission that sometimes you just have to massage the numbers. You have to tweak the counts to account for the fact that your training data will never be perfect and it will never be infinite. The choice of the model, how you frame the problem in the first place, often matters more than just the raw amount of data you have.
It's that blend of hard science and, well, intuition. Knowing when to trust the math and when to smooth over the rough edges.
That is the essence of statistical NLP.
Well, that wraps up this deep dive into the statistical machinery of language. A big thank you to Samuelson and Tajner for the guide, and thanks to you for listening.
See you next time.